Welcome to Lesson 3 in Linear Algebra, Math 260. In this lesson we'll cover the vector norm, or length of a vector, and the rule for cosines. So in our previous lesson we learned how to compute the dot product, and we're going to make use of it in this lesson. So let's begin with the introduction here. The length of a vector in R2 in the Cartesian plane is easy. It's based on the Pythagorean theorem, because if a vector has coordinates AB, then A is the x coordinate and B is the y coordinate, as illustrated here. So the length of the vector is actually the length of the hypotenuse of a right triangle. And so we know how to do that. The square of the length is a squared plus b squared, because that's the square of the hypotenuse. So the length itself is the square root of a squared plus b squared. But remember, when we take the dot product of u with itself, we get a times a plus b times b. We get precisely a squared plus b squared. And so it's really the square root of u dot u. And we can extend this also to vectors in higher dimensional spaces. Given a vector u with coordinates x1 through xn is an element of the vectors in n-dimensional space, then the length of this vector is defined to be the square root of the sum of the squares of the elements, or the square root of the sum of the squares of the coordinates. And that again is just the square root of u dot u. Now we can prove this theorem using mathematical induction on the dimension of n. That is, assuming that it works in two-dimensional space, then the length of one of the legs can be added to the length of the two-dimensional space to get one in three-dimensional space, etc. But we won't go into the details of that proof here. Now, often when we're computing elements geometrically, it's enough to know the square of the length instead of the length. When we do this, we can avoid the square root and compute the square of the length as simply the dot product of a vector with itself. And this can be handy. It can give us exact answers without the need to take square roots. So some examples. Given the vector with coordinates, the x coordinate of 3 and the y coordinate of 4, the length of this vector is the square root of 3 squared plus 4 squared. Well, that's 9 plus 16 is 25. The square root of 25 is 5, so the length of this vector is 5. Given a vector with coordinates 7, 7, the length is the square root of 7 squared plus 7 squared. That's 49 plus 49. But now we can factor out a 7 squared. And so we end up with 7 times the square root of 2 as the length of this vector. And one more example. Given a vector in R4, four-dimensional space, with coordinates 1, 2, 3, 4, its length is the square root of the sum of the squares of the elements. So 16 plus 9 plus 4 plus 1 is 30. That's the square root of 30, or approximately 5.47. So one way to use the length of a vector is to create what's called a unit vector. A unit vector is simply a vector of length 1. That is, it has what we'll call this symbol, the norm of u is 1. So it's not too hard to see that if u is any non-zero vector, we can create a vector of length 1, a unit vector, in the same direction by simply scaling u by 1 over its length, that is, dividing u by its length. So the symbol we use for a unit vector is u hat, or with a caret over it, and we create it as the original vector divided by its length, or the original vector divided by the square root of the dot product of the vector with itself. Again, an example will be helpful. If we have the vector u with the x element, or x coordinate, is 5 and the y coordinate is 12, then the length of the vector is 5 squared plus 12 squared. That's 25 plus 144 is 169, and the square root of 169 is 13. So the length of this vector is 13 units. So a unit vector in the same direction we get by scaling the original vector by 1 over the length, that is by 1/13. Now remember, when we looked at vectors originally, when we scale a vector, all it does is change the length of the vector, but it doesn't change the direction. So this unit vector points exactly the same direction as the original vector u, but it has length 1. So if we multiply through by 1/13, we get 5/13 as the x-coordinate, 12/13 as the y-coordinate, and you should verify that the length of this vector is 1 by computing 5/13 squared plus 12/13 squared. Now that we have a way of algebraically computing the length of a vector using the coordinates as we've just seen, we can rewrite the geometric dot product that we had in the previous lesson as the dot product of two vectors uv is the product of the length of the first one, or the norm of the first one, times the length or norm of the second vector times the cosine of the angle between them. Now this particular form is most useful when we know the coordinates or the elements of the individual vectors, because then we can compute the dot product using the sum of the products of the corresponding elements, and we can compute the lengths as we saw above using the extended Pythagorean theorem. So the only thing we don't know in this equation is the cosine. So we can solve for the cosine, and we see that the cosine of the angle between two vectors is the dot product of the vectors divided by the product of their lengths. And that's the same as the dot product of the unit vectors that go in that direction, because we have u over the norm of u dotted with v over the norm of v. So this is a handy formula for determining the angle between two vectors, even if they live in higher dimensional space. So here's a simple example. If the first vector is 1, 0, that is the x component is 1 and the y component is 0, that's a vector that points in the x direction. And v is a vector with coordinates square root of 3 over 2 for the x coordinate and 1/2 for the y coordinate. We can determine the angle using the formula we just had above. First we compute the dot product of these two vectors. It's 1 times the square root of 3 over 2 plus 0 times 1/2, so the dot product is just the square root of 3 over 2. The length of the first vector is easy. It's the square root of 1 squared plus 0 squared, which is just 1. The length of the second vector v is a little trickier. It's the square root of the square root of 3 over 2 squared plus 1/2 squared. Well, when we square the square root of 3 over 2, we get 3 over 4. And when we square 1/2, we get 1 over 4. So 3/4 plus 1/4 is 1, and the square root of 1 is 1. So this vector also happens to have a length of 1. So now it's easy to use the formula we have just shown above, that the cosine is the dot product of the vectors divided by the product of their lengths. In this case, the dot product is simply the square root of 3 over 2, and the lengths are both 1, so the answer is the square root of 3 over 2. So this is the exact value of the cosine of the angle, and this is one of our special angles. When the cosine is square root of 3 over 2, we know that we're sitting at 30 degrees, or pi over 6. We'll do another example that doesn't come out so nicely. Given a vector u in three-dimensional space, that is a vector in R3 with coordinates 4, 2, and -1, and a vector v with coordinates 3, 6, and 5, we can determine the exact value of the cosine between the two of the angle between the two vectors, and also the approximate angle. And very often in computations, it will be enough to know the cosine of the angle. We won't need the exact value of the angle. So again, the cosine of the angle between these two vectors is the dot product of the vectors divided by the product of their lengths. So the dot product is, as we've grown accustomed to doing, the product of the corresponding elements added together. 4 times 3 is 12, plus 2 times 6 is 12, that's 24, minus 5 is 19. So u dot v is 19, and then the length of u is the square root of the sum of the squares of the elements. So 4 squared is 16, plus 2 squared is 4 is 20, plus negative 1 squared is 1. So the length of u is the square root of 21. The length of v is 3 squared is 9, plus 6 squared is 36, that's 45, plus 5 squared is 25. Add those up, we get 70, so the length of v is the square root of 70. So now we can determine the exact value of the cosine of the angle between these vectors. It's the dot product, 19, divided by the product of the lengths, the square root of 21 times the square root of 70. And notice there's a factor of 7 in both of these values, so we can take out 7 squared. The square root of 7 squared is 7, and we're left with 3 times 10, or 30. So this expression 19 over 7 square roots of 30 is the precise value of the cosine of the angle between those vectors in three-dimensional space. We can use a calculator's arcsine function, or arc cosine or inverse cosine, and we can see this angle is approximately 60 degrees. Now in this three-dimensional figure, we've actually drawn those vectors in three-dimensional space, and we can see that that angle looks like approximately 60 degrees. Now it's your turn to practice. So we're given two problems. The first, we're given the length of vector u and the length of vector v and the angle between them. We want to determine the dot product. So without the coordinates, if we know the lengths and we know the angle, we can determine the exact value of the dot product. And then in the other case, where we're given the coordinates of these two vectors u and v, you're asked to determine the exact value of the cosine. It won't be possible to get the exact value of the angle, but by the way the formula is set up, you can get the exact value of the cosine. So please work these problems. Pause the video now, do the exercises, and then we'll compare our solutions. Okay, hopefully you found that that wasn't too difficult. Let's compare our answers. So in the first case, by the cosine formula for the dot product of u and v is the product of their lengths times the cosine of the angle between them. Well, we're given the lengths, so it's 7 times 12 times the cosine of pi over 6. Well, the cosine of pi over 6 is the square root of 3 over 2, so when we do the arithmetic, we get 42 times the square root of 3 as the exact value of the dot product of these two vectors. For the second problem, we can compute the dot products and we can compute the lengths, so we can determine the cosine using the other version of this formula. The dot product of the two vectors is easy. It's 3 times negative 2 plus 2 times 4 plus 5 times 3. If you do the arithmetic with care, that's 15 plus 8 minus 6 is 17. And then the length of the first vector is the square root of the sum of the squares of the coordinates. So 3 squared plus 2 squared plus 5 squared is the square root of 38. And the length of the other vector is the square root of the sum of the squares of the elements. So minus 2 squared plus 4 squared plus 3 squared, that's the square root of 29. So we can put it all together. The cosine is the dot product divided by the product of the lengths. That's 17 over the square root of 1102. The approximate value, I guess we can spell that right, the approximate value of this is about 0.512 as shown there. Okay, well hopefully you got something like that, or this review was helpful. Let's look at our homework. So for homework, please download and study the notes for Lesson 3. That's the vector norm and cosine rules you can find on D2L. This material is also covered in section 6.1 of our textbook. And on Wednesday, we'll work more exercises applying all we know about the dot product and vector arithmetic. And then this week on Friday, we'll get practice with all the lessons we've had about vectors and have a comprehensive quiz on this material. Okay, that ends our lesson for today.